Welcome to lecture 20. So in the last class we were discussing great orthogonality theorem, and let me write down the expression for great orthogonality theorem again. So this is summation over all R again, where R is the symmetry operation in a particular point group, and then tau I is the ith irreducible representation, and this represents the mth row and nth column matrix element under symmetry operation R for a ith representation. So that means this particular is a matrix element, and this is a second matrix element which is represented by jth under the same symmetry operation R with different mth and nth elements, and this is given by h over li lj with Kronecker deltas of delta ij m m prime and n prime. And of course we did not discuss this in the last lecture, but one of the factors will be a complex conjugate if we are dealing with complex numbers here. So the matrix elements can take complex numbers. We will see that when we will come to cyclic groups. So in this, when we are having complex numbers in matrix elements, we have to take complex conjugate for one of the factors here, and rest of the theorem remains same. So let me see, it represents complex conjugate when dealing with complex numbers. Okay, so now let us see how do we use great orthogonality theorem, or GOT as we call it, to actually identify whether a particular representation is reducible or irreducible. So sometimes it is difficult to find out by block factorization, so we can easily use GOT rules in that case, and we'll see how. So let us again take the case of water molecule, and let us develop representation. We don't know whether it is reducible or irreducible, but let us take the basis set as this is my phi, which is the basis set, as 1s orbital of HA. Let's call it as HA, and this one is HB. 1s orbital of HB and 1s orbital of oxygen. This is my basis set. So basis set is these three orbitals. So let us try to take these basis sets and develop a representation. Again, we don't know whether it's a reducible or irreducible representation. Okay, so the dimension of the matrix will be 3 cross 3 because number of bases is 3. So point group is C2V E, and let's call it as tau m. Because the dimension is 3 cross 3, E will be a unit matrix of order 3, right? So this we have seen every time. So E will always be a unit matrix of a particular order, and the order will be defined by the number of basis sets in the basis set vector. Now that means the trace under E will define the order of the irreducible representation, or the dimension of the irreducible representation, which is defined by Li. So in this case, if we take the trace under representation E, any matrix under E, the trace will come out to be 3, and that 3 will be the dimension of tau m. In this case, Li is equal to 3 because trace of matrix under E will be 3. Okay, so this is just to highlight because we'll be using this property later. So C2Z. Now can you think what will be this thing? So if I'm taking HA, HA will be replaced with HB. That means this will be 0, 1, 1, 0, and Z, or 1SO remains same, so this will be 1SO. Okay, now for sigma xy, or we can call it as, in this case, sigma v1, and then we have sigma v2. Okay, so let's see what is sigma v1. So let's say sigma v1 is the one which is perpendicular to the plane. Okay, so again sigma v1 SO orbital will remain as it is, so it will be 1. Now S HA and HB will be reflected, so we'll have 0 1 1 0. Okay, now for sigma v2 it will be the molecular plane, so everything will remain at its own place, so that means this will be like a unitary vector, or the identity matrix, right? 1 0 0 0 1 0 0 0 1. So now let's say if we want to reduce this, let's say if we it looks like as a reducible representation. Why it looks like a reducible representation? Because I can see that this can be easily block factored in 2 cross 1 and 1 cross 1 matrix, right? You cannot block factor into 1 cross 3 1 cross 1 because this one is a square matrix of 2 cross 2 order. So I can block factor it by 2 cross 2 and 1 cross 1. But can it be further reduced? Okay, so let's say if I block factor it and write it as tau 1 and tau 2, which is 1 0 0 1 and 1, then I write it as 0 1 1 0 and 1 0 1 1 0 1 1 0 0 1 and 1. So at this point I know that this one is a irreducible representation because this is already of the order 1. You cannot reduce this further, so this is irreducible. Now whether this is a reducible or irreducible, I don't know. I can always say that, let's say like in the case of C3V, x and y are not separable. So I can say that these two are the basis, whatever is the basis set for this representation are not separable in this particular case, and that's why it is giving me a 2D representation, right? Two-dimensional representation. So this can be a irreducible representation, but this can also be a reducible representation if we manage to find matrix such that we can carry out a similarity transformation to convert into a diagonalized matrix, and that is a tedious process. So we don't know whether a u prime exists such that a similarity transformation of this will convert into block diagonalized matrix of 1 cross 1, right? So in that case we'll be again able to reduce it further to 1 cross 1 matrices, right? But we don't know at this point whether it is possible or not. So let us try to apply the GOT properties to these two representation, considering that it's a IR representation. So this GOT applies only to IR representation, that is irreducible representation. So if these properties, which is defined by this particular equation, this equation, if these properties are valid on these two representations, that means both of them will be IR representation. If these properties are not valid, then we can say that this is not a IR representation. This we already know that it's a IR representation. Okay, so let us try to find out how to do that. So let us try to calculate summation over all R tau 1 R 1 1, okay, and tau 2 R 1 1. So what should be the value of this? in two different representations, if we are taking the same corresponding matrix element, the product should come out to be 0. So let's see for our case whether it comes out to be 0 or not. So under all symmetry operations, we have to take the product of the corresponding matrix elements. So that means this, this into this, right? So 1 into 1, 0 into 1, 0 into 1, 1 into 1. So that means 1 into 1 plus 0 into 1 plus 0 into 1 plus 1 into 1. This should turn out to be 0. However, we are getting this as 2, which is not equal to 0, right? So this tells us that since this product is not going to 0, that means the GOT property is not valid. And we know that tau 2 is irreducible representation. This implies that tau 1 is not a irreducible representation and can be reduced further. Okay, so let's also consider the case we already know that we have seen for water the set of irreducible representations are obtained by unit vector transformations, right? So we got 4 such representations, which was 1 1 1 1, 1 1 minus 1 minus 1, 1 minus 1 minus 1 1, 1 minus 1 1 minus 1. So now if we apply the same property, so let's take the product of any two matrix elements and take the sum. This will always come out to be 0. So let's do this. 1 into 1 plus 1 into 1 plus 1 into minus 1 plus 1 into minus 1. This will be 0. So you can test any of these two. All 4, tau 1, tau 2, tau 3, tau 4 will be orthogonal to each other, which satisfies the rule of GOT, right? So I can say that tau 1 dot tau 2 equals 0, tau 2 tau 3 equals 0. Any two products you can take in this case, right? Everything will be equal to 0. So that tells that the rules of GOT are valid in this case. So this is how you can test any given representation for whether it's a reducible or a irreducible representation. Okay. So that's one very nice application, and let us now look at the 5 properties which we will be using to develop IR representations for a given point group. So 5 properties of GOT. Okay, so the first property is sum of the squares of the dimensions of an IR representation of a point group is equal to the order of the group. Order of the group is H. So what does it say? That sum of the squares of dimension of an IR representation. So dimension of the IR representation is denoted by Li. So that is Li square for various i's is equal to H. In other words, we can say that L1 square plus L2 square plus L3 square is equal to H, right? Or we can also say, since the character or trace of the E operation is equal to dimension of the IR representation. Now we know that the character or trace of the matrix for E operation is equal to dimension of the IR representation. So we can always say character of E square summation over all I is equal to H, right? So this will be summation over all I. So this is our first property. So we will see the use of different properties, and we will not provide proof of all the properties because that is not in the scope. But for a couple of properties, I will provide for which the proofs are straightforward. Rest of the proofs you can actually find in different mathematical group theory books, but these proofs do not concern in the applications of group theory to chemical applications, so that's why we are not including here. So let's look at the second property. So second property says the sum of the squares of the character of any given IR representation is equal to H. Mathematically speaking, sum of the squares, that is character of under any operation and square of that under all operations is equal to H. So if you are taking trace of a matrix under a particular symmetry operations and we square it and take the sum over all symmetry operations, what we will get is H. So let us try to prove this one because the proof is straightforward. So let us do this. So let's start with GOT, which is summation over all R tau I R Mn and tau J R M prime N prime is equal to H over Li Lj delta Ij delta mm prime delta nn prime. So I'm not putting the complex conjugate, or you can actually put complex conjugate also here, so that doesn't matter. Okay, for a given IR representation we can say that I is equal to J, right? Because it says for any given IR representation. So we are not taking product of two different IR representations. We are just considering here single IR representation. That means I is equal to J here. So let's do that. So what we will get is summation over all R tau I R Mn tau I R M prime N prime, and so let's drop the star here because we are not considering any complex conjugate, or if there is a complex conjugate you can consider star, doesn't matter here. So delta Ij term is gone because that will be equal to 1, and Li and Lj will become Li square, so the square root will cancel, so you will have H over Li and delta mm prime delta nn prime. Okay, now because we are interested in trace, so we have to consider only the diagonal elements. So for diagonal elements, what will be the condition? M will be equal to n and m prime will be equal to n prime. So that means we are getting rid of one set of indices here. So this implies summation over all r tau I r. So put m equal to n. So you have m and tau I r, m prime equal to n prime. So you will have m prime, right? So now you don't have that index. So there is no point writing the Kronecker delta for this. So m prime. So that goes, right? So equation is reduced. For diagonal elements, we have this. Now from diagonal elements, if you have to go to trace, then we have to sum over all m. We'll get trace of this matrix. If we sum over all m prime, we will get sum of this matrix. So what we'll do is we will take summation so on both sides. We will take summation over all m and summation over all r, all m prime. And we already had summation over all r. So what do we have? Tau I r tau I r m prime, and this will be equal to summation m prime h over li delta m prime, right? Now this summation only applies to first term because the index is m index is only over here. M prime will apply only to this one. So we can take these summations inside. So we will have summation r, summation m, we can write this as tau I r and summation m prime tau I r m prime, right? Now let us expand one of these summations. So if we open this summation, so let's say h over li summation m. So this becomes delta m1. So I'm expanding m prime from 1 to li, right? Plus delta m2, delta m3, and so on. This goes up to delta m li because that's the dimension of the matrix, dimension of the IR representation. That means dimension of the matrix. So m prime varies from 1 to li, right? So this is 1. Now let's say this particular term is equal to, this is equal to trace, this is also equal to trace, right? So we have got what we wanted on the left hand side. So what we have here is summation over all I, trace of ith representation under the operation r, and this is also trace of ith representation under operation r. So this becomes square, right? And we wanted this to prove at the left hand side was this, right? Now let us see how do we get h out of this. So h upon li. Now let's try to expand summation m over here. So let's take the delta m1, the first term here, and expand. So this will be delta 1 1 plus delta 2 1 plus delta 3 1 and so on delta li 1. That's my first term. This comes as a result of expansion of this one. Similarly, for delta m2, we will have delta 1 2 plus delta 2 2 plus delta 3 2 plus delta li 2, right? So this comes as an expansion of this one. Similarly, we can keep on going, and then for last one we will have delta 1 li plus delta 2 li plus delta li, right? Now, if you notice, each of this term will go to 0 except where the indices are same. So delta 1 1 will remain as 1 and rest all will go to 0. So that means out of each bracket I will get 1, right? So h upon li, I get 1 from here, I get 1 from here, because again 1 2 will be 0, 3 2 will be 0, and so is li2. Only delta 2 2 will survive. Similarly, from the next term, delta 3 3 will survive, and then here delta li will survive. So I will keep on getting 1 up to li times, because the dimension of this was li. So originally it was li. So we will get li times 1. This implies that we will get li over here, h over li into li, which is equal to h. That is the square of the trace under any symmetry operation over all symmetry operations is equal to h. All right. So that was easy to show. Now let's look at third property. So we will quickly see third, fourth, and fifth property, and then we will do illustrations of these properties in the next class. So now it is saying that the vectors whose components are characters of two different IR representations are orthogonal. So again, let us start with the statement of GOT, and then we will keep on simplifying that. Mn and tau j r m prime n prime is equal to h over. Again, I'm dropping star over here. Explicitly, I'm not writing every time, but I mean it is there if we are using any complex number. So for two different representations, we know that I is not equal to j, right? This implies that our right hand side goes to 0. We already know that, because I is not equal to j, delta ij will be equal to 0, turning everything else equal to 0. We don't care about now what happens here, right? Now for the left hand side, if I is not equal to j, we can write it as right. Now again for diagonal elements, what you do is equate m equal to n and m prime equal to n prime. We can do that because we are only choosing diagonal elements out of this. So once we do that, and then we take for trace, if we take summation over all m and summation over all m prime, we will get trace. Like in the last property, we saw that this is equal to nothing but square of trace under representation, under ith representation for a particular symmetry operation, and square of this. And right hand side, we have already seen that it is equal to 0, right? So this was very simple to prove. Basically, left hand side was very similar to the second property too, and right hand side is very simple to show that it is equal to 0 because delta ij, I is not equal to j, so everything goes to 0. So let's look at the fourth property. Again, fourth property we have already shown before. In a given representation, now this can be reducible or irreducible. So that's why it says in a given representation, the characters of all matrices belonging to operations in same class are identical, right? So what I'm saying is, in a given representation, the characters of all matrices belonging to operations in same class are identical. We have already seen that operations under same class are related to each other by similarity transformation, and similarity transformation does not change the trace. So that means the character or the trace of the matrix will not change. So there is nothing to prove here. We have already shown this by showing that the trace of a is equal to trace of a prime, where a prime is equal to, right, this we have shown. Trace of a is equal to trace of a prime, which is, trace is called as character here, where a prime is nothing but u inverse a and u. So there is nothing to prove here, but this can also be shown as a proof from GOT. We have shown it using non-GOT, but GOT can also be used to show this. Again, we are not going to discuss this. And the fifth property, which is derived from GOT, is that the number of IR representations in a group is equal to the number of classes. This also we have seen. So these are the 5 properties of great orthogonality theorem, and we have seen couple of proofs, but rest of them we are just using the properties as is. So now we should be well aware of what each property is saying, what is the meaning of each property. So please go through it nicely, and then in next class we will be dealing with some examples of how to use these properties to write character table, or in other words, write the irreducible representations, all the irreducible representations of a particular point group, without actually worrying about what is the basis set, what are the symmetry operations, what are the effect of symmetry operations. Nothing we are going to do. We are just going to write directly the character table or the trace or the irreducible representations directly. So this theorem is very, very important. So try to go through it once again, all the properties, and let's discuss again in the next class how to implement these properties to write down various irreducible representations. Thank you.